A sphere is a two-dimensional surface embedded in three-dimensional space. Intuitively, turning it inside out without creating a hole seems impossible, violating basic spatial intuition. Yet differential topology proves this transformation, known as sphere eversion, is possible. Stephen Smale first demonstrated this existence theorem in 1957, shocking the mathematical community because the process requires the surface to pass through itself, temporarily losing its embedding property while maintaining smoothness. This transformation is an immersion, not an embedding, meaning the surface remains locally smooth and differentiable throughout the entire process. The key constraint is maintaining a well-defined tangent plane at every point during the continuous deformation. Eversion requires a regular homotopy, which is a continuous sequence of immersions connecting the initial sphere to the final, inverted sphere. An immersion ensures that the derivative map is injective everywhere, meaning the surface is locally flat and smooth. Crucially, the surface must never be torn, punctured, or creased. The Gaussian curvature must remain finite everywhere. The challenge lies in reversing the orientation of the normal vector field continuously. The initial sphere has an outward-pointing normal vector. The final sphere must have an outward-pointing normal vector relative to the new interior, effectively reversing the original orientation through the continuous path of immersions. Smale's initial proof was purely existential, relying on the classification of immersions. The primary obstruction to eversion is the change in the normal vector field, which relates to the second Stiefel-Whitney class of the normal bundle. Smale showed that for the two-sphere in three-space, this obstruction vanishes. The key insight is that the space of all immersions of the two-sphere in three-space is path-connected, meaning any immersion can be continuously deformed into any other, including the one with reversed orientation. This result is a specific case of the H principle, which states that formal solutions to certain partial differential relations can often be deformed into actual geometric solutions.
Since tearing is forbidden, the only way to reverse the orientation is by allowing the surface to intersect itself. These self-intersections are necessary singularities in the immersion path. The surface must pass smoothly through itself, creating a curve of self-intersection where the surface is locally non-injective. The simplest conceptual self-intersection involves a moment where two parts of the surface meet tangentially, but smooth eversions typically involve more complex self-intersection curves. The eversion process requires at least one point where the surface is locally non-injective, meaning multiple points on the original sphere map to the same point in three-space, temporarily violating the embedding condition. The first explicit symmetric visualization of sphere eversion was developed by Bernard Morin in the 1970s. The Morin surface is a highly symmetric intermediate stage in the eversion process. It possesses a four-fold rotational symmetry and is characterized by a single circle of self-intersection. This specific immersion demonstrates that the eversion can be achieved with minimal complexity in terms of symmetry and self-intersection structure. The Morin surface is often used as a benchmark for visualizing the minimum number of critical points required for the regular homotopy, providing a concrete geometric realization of Smale's abstract theorem. Another conceptual approach, popularized by William Thurston, involves the half-turn method. Imagine cutting a small hole in the sphere and pushing the boundary inward, creating a neck. The eversion is achieved by rotating the neck 180 degrees and then sealing the hole back up. While this description involves a temporary boundary, the full smooth eversion is achieved by continuously deforming the surface to mimic this rotational action without ever creating a physical boundary or tear. This method highlights how local rotation of the surface structure can globally reverse the orientation, providing an intuitive pathway for the complex topological transformation.
The orientation reversal is mathematically tracked using the Gauss map. The Gauss map assigns to every point on the surface its unit normal vector, mapping the sphere to the unit sphere of directions. For the initial sphere, the Gauss map covers the unit sphere once. For the everted sphere, the Gauss map covers the unit sphere once, but with reversed orientation. The eversion process corresponds to a path in the space of immersions, where the degree of the Gauss map changes from +1 to -1. The degree of the Gauss map must pass through 0 at the moment of maximal self-intersection, indicating the temporary loss of global orientation. The complexity of an eversion is measured by the number of critical points of the height function during the process. The minimum number of critical points required for a smooth eversion of the two-sphere is 4. These critical points correspond to moments where the surface momentarily flattens or changes its topological structure relative to the ambient space. The existence of an eversion with only 4 critical points was proven by Francis and Morin, demonstrating the efficiency of the transformation path. Minimizing these critical points is crucial for creating the most elegant and efficient visualizations of the eversion process. The possibility of eversion depends heavily on the dimension of the embedded manifold and the ambient space. The Smale-Hirsch theorem, a generalization of Smale's result, addresses the existence of immersions and regular homotopies in higher dimensions. For the n-sphere embedded in Rn+1, eversion is possible if and only if n is even. For example, the 1-sphere, a circle, in R2 cannot be everted without tearing, but the 2-sphere in R3 can. The 3-sphere in R4 can also be everted, following the same principle of allowing self-intersection while maintaining smoothness, confirming the pattern for even-dimensional spheres. Sphere eversion is primarily a foundational result in differential topology, demonstrating the flexibility of smooth manifolds. It has applications in visualizing complex topological concepts and serves as a powerful example of the H principle in action, showing that local conditions often determine global existence. The techniques developed to visualize and prove eversion, such as the use of regular homotopies, inform research in knot theory and the study of minimal surfaces. The process challenges intuitive notions of space and provides a concrete example where local smoothness overrides global embedding constraints, expanding our understanding of geometric possibilities.